generally your hub is going to need to have bigger bandwidth than your spokes, because say at any given time that each of these spokes starts transmitting its full available data rate. This one's 128, this one's 512, this is 64. Your hub is going to have to be able to absorb all that, and we're going to get into this in a lot more detail when we start looking at traffic shaping. Okay, well, not all is perfect in the hub and spoke world. There are some cons. Probably the biggest one is that all traffic between the spokes is going to have to traverse that hub. So remember, we went to the example of R2 speaking to R4. It would have to go through R1 and then back out into R4, and then through R1 and back out to R2 to talk to each other. So you're adding a hop there, and this can run into some problems depending on network speed, or in a lot of cases geographical distance between devices. We'll talk about that more in just a little bit here. You do have a single point of failure for the entire network, and that point of failure, let's pop back here again, is going to be that access circuit on R1, which is your hub. So if the hub goes down, you have no communications, and that draws from the fact that all spoke-to-spoke communication has to go through the hub. So even though R2 can be up and R5 can be up, if there's a power outage at R1, now you don't have any communication between any of these devices. So that's one of the big downfalls of a hub and spoke design. Whereas if one of the spokes go down, well, yeah, of course communication that spoke is down, but the rest of your network is up. And then the final one is that routing between spokes can be prevented by the split horizon rule. We'll get into this a whole lot more detail when we start talking about how different routing protocols work with hub and spoke frame relay networks. But let's pop back once again. And actually this time let's take a look at a little simpler topology. We're only going to have 3 routers here, but still a hub and spoke. Here's our hub, here's our 2 spokes. So what split horizon does is it says basically, and I've heard this from Scott Morris, who's a famous CCIE instructor. I like his analogy the best. Basically, don't tell a joke to the guy that just told you the joke. So in this case, let's imagine that there's a network down here on R3, and you're running a routing protocol here. So R3 advertised that, let's just call it network X. It says, R3 says to R1, hey, if you need to get to network X, come through me. R1 gets it and says, okay, well fine. Let me go ahead and advertise that out to R2 so that he knows about it. Well, depending on the design, and we'll find ways around this, but if this is one physical interface with both virtual circuits on it, the routing is going to treat that as a single interface. So it's going to say, well, you know what, I learned the route to network X in through serial 0/0 on R1. Now to reach R2 to advertise this, I have to go back out serial 0/0 on R1, and I can't do that because that's where I learned that route from, and split horizon is going to prevent me from doing that. Basically, I think that I'm telling R3 the same joke that it just told me a second ago. So again, we'll go through this in a whole lot more detail when we're going through routing with frame relay, and also when we're actually configuring this. There's many ways around this in the routing protocols as well as in your design, whether you're using point-to-point sub interfaces or physical interfaces, and we'll get into that in more detail in just a bit. But just wanted you to know that that is one of the disadvantages and something you're going to have to plan for when you're designing a frame relay hub and spoke network. So this note down at the bottom, it says most hub and spoke designs will add some redundancy between endpoints, essentially making the design become a partial mesh design. Like I said, almost all of your networks are going to become partial mesh designs. You're going to utilize the advantages that frame relay has with a hub and spoke design, but when you want to add redundancy, let's go back again. When you want to add redundancy to your network, you can always add another virtual circuit. So let's say that R2 is a regional headquarters and R1 is your national headquarters, and you're saying, well, you know what, I need guys from R4 and R5 to have a dedicated connection from R2. So you can put that in. That provides redundancy. It also gets around sending that traffic directly to the hub. So you can have a hub and spoke, and then as soon as you add some redundancy to it, it's not technically a hub and spoke anymore. At that point it becomes a partial mesh. But again, like I said, almost all your designs are going to be partial meshes anyways. I guess my point is you're not locked into a hub and spoke design. You don't say, okay, I'm going to design a hub and spoke design, and then you're locked into it. It's like, okay, well, I can't change this to be a partial mesh by adding another virtual circuit in there because there's some iOS dependency or some physical interface dependency. Very easy to change and scale this design. Alright, before we wrap up this lesson, I wanted to show you a hub and spoke frame relay network in action for a couple of reasons. One, it's been a long time since we've seen the CLI. I had a couple of theory lectures, and that's primarily what this one is. And the second one is I want to show you a potential downfall with hub and spokes that you're going to want to be aware of before you start designing these. So let's take a look at the network. We're going to have R1, that's going to be our hub, and we'll just call this our corporate headquarters. And then we've got R2 and R3. Those would be our remotes or spoke. Now, the interesting bit here, it's going to harken back to the first lesson. We're looking at the DELC assignment. So we have an access circuit, full T1, hitting the frame relay cloud for R3. And everything here is going to go on DELC 301. The DELC is the layer 2 addressing scheme for frame relay. So we've been assigned 10.1.123.3/24 is our IP address. So if we want to communicate with the .1 address on that subnet or the .2 address on that subnet, we send it out this interface. We only have one path, so we're going to send everything on DELC 301. Same thing with the R2. It's going to go out 201. Now the hub is where it gets interesting because we have a single physical interface, 00/0, and we have an IP address assigned to that interface. But we have to communicate out that interface to each of these devices. So how do we know which way to send this? If I'm trying to communicate with R3, I know which interface is going to go out. It's going to go out 00/0, but the same thing with R2. What it's going to do is it's going to have a mapping, and we'll go through mappings ad nauseum later on. We'll actually have a special lesson specifically for mappings. But basically what it's going to say is it's going to say if you need to get to this IP address, this .3 address, go out DELC 103, and the cloud's going to know to send that to R3. If you have to get to the .2 address, use 102. So that's one of the interesting bits with frame relay, and one of the things that's a little different, especially if you're coming from, configuring point-to-point connections, is that you can have multiple virtual circuits existing on the same physical frame relay interface. Now, when I get into this, there's probably going to be some of you that are aware of frame relay configurations, and you're going to say, hey, that's not a best practice. I know this is not a best practice. That's another lesson, just showing you this in action. So the issue with spoke-to-spoke communication is that if R3 wants to talk to R2, as we discussed earlier, it has to go through R1. So what's going to happen is it's going to send this packet to the .2 address. It's going to go out DELC 301, and not going to get too heavy into mappings, but basically since that's the only DELC it can traverse, it has to have a mapping for this IP address on 301. So it'll have two mappings, one to the .1, which is hub, and one to .2. It'll go up to R1. R1's going to go ahead and send it back out 00/0, but it's going to send it out on DELC 102. And it's going to get to R2. Same thing going back. R2 would send it out 201. It would get to R1. R1 would send it out 103, and it would get to R3. You might be thinking, well, where is the split horizon rule? That doesn't come into effect yet because we're not actually routing. This is a physical connection. These guys are all on the same subnet, so we're not going to have to route anything. These are basically just directly connected routes. Anyways, I'm going to keep this guy up while I bring up the CLI here. And let's go ahead and pop over to R3. What I'm going to do here is I'm going to ping the hub 10.1.123.1. I'm going to send a ton of pings. 10,000, should that be enough? It's going to take a while to do this. Well, actually, while it's thinking, let's go back over here and take a look at the diagram. So right now we're pinging from R3 to R1. We're sending 10,000 pings that way. Next thing we're going to do is we're going to ping from R3 to R2. And remember that any spoke-to-spoke communications on a hub and spoke network will have to go through the hub. So if you're looking at this, can you guess what the difference in behavior is going to be? Keep that in mind. Let's go back, and so we've completed that. Let's go ahead and let's just pop in R2, and I'm going to pause while it sends 10,000 pings from R3 to R2. Okay, I really didn't need to send 10,000 pings. I could have got away with a lot less. Just in case you're wondering, if you haven't run across this before, what I did was I pinged the address, and then RE is just short for repeat. So if you ping an address, normally it's going to send 4 ICMP packets. In this case, I wanted to send more than that, so the keyword here, re, is short for repeat. It's saying send 10,000. And the reason I want to do that is I'm doing this on Dynamips, and even if I wasn't doing it on Dynamips, there's not a geographical distance between these devices. It's significant. So what I wanted to show you is that here's our ping results going from spoke to spoke, and our fastest was 1 millisecond, our slowest was 100 milliseconds, but we're looking for this average, and that's why you want to send more than 4 packets. Generally, whatever you feel good with, 100,000, depends on how slow the connection is, but the more packets, the more accurate this average is going to be. So now if we scroll up, and hopefully I've got enough scroll buffer, and I do, we can see this is our pings from R3 to R1, which is the hub, and the minimum was 1 millisecond. Don't buy that, but whatever. Maximum was 76 milliseconds, and our average was 3. So it didn't get to where I wanted it to be. Because we're looking at such small distances, there's not going to be significant time. What I wanted to show you was a difference. So it's 3 milliseconds here, and 4 milliseconds down here. Basically, whenever you ping from spoke to spoke, it's going to be a longer path and it's going to take more time. If R3 is 2 milliseconds from R1 and you ping, obviously your average is going to be 2 milliseconds. Now, let's say that R1 is 2 milliseconds to R2. Your ping time from R3 to R2 is going to be the combination of these two times. So it's going to go 2 milliseconds to get here, 2 more milliseconds to get here, and that's what I was trying to show you. It should be exactly double, realistically, in this case. But we're talking about such small amounts of latency. We're talking about milliseconds here. So you probably think to yourself, yeah, big deal. I know that the end-to-end delay is going to be the culmination of each of these virtual circuits. The thing is that when you're provisioning this, if you have two routers that are geographically close to each other, like if this is Los Angeles, this is Minneapolis, and this is New York, not a big deal if you send all your traffic from New York through Minneapolis. Now, if this is Los Angeles, San Diego, and Minneapolis, San Diego and Los Angeles are pretty close to each other, so the delay that you're going to incur sending traffic up to Minneapolis and then back down to San Diego is probably going to be longer than what you would get if you had a direct connection, and you could do it with a point-to-point connection if you so choose, or just add another virtual circuit here going from R2 to R3 so that it doesn't have to traverse that hub. So that's something when you're looking at designing that you want to keep in mind, that even though you're saving some money here, if these guys are geographically close enough, then you may just want to go ahead and throw a direct connection in here rather than throwing everything through the hub. Because in our example here with San Diego, or this is Los Angeles, this is San Diego, doesn't matter, it might be 25 milliseconds round trip between these two nodes. That's probably even high. But it might be 30 milliseconds to Minneapolis and another 30 back to San Diego. So your round trip from Los Angeles to San Diego would all of a sudden be 60 milliseconds when it could be half that, just going directly connected there. So again, keep that in mind when you're designing for frame relay hub and spoke network. Alright, let's wrap this guy up. One of the main benefits of frame relay over point-to-point leased lines is that you can achieve cost savings by both reducing the amount of equipment that you need to purchase as well as the cost for circuits. But in order to take advantage of these savings, you want to know how to incorporate these benefits of frame relay into your network design when you're designing frame relay networks. It's certainly possible to design a full mesh using frame relay, but that's not where you're going to get the most advantage from frame relay. You're going to want to at least take a look at the hub and spoke design, and that's going to primarily be your design, whether it's a pure hub and spoke or a hub and spoke with some redundancy built in, which then becomes a quote-unquote partial mesh. There are big advantages to the hub and spoke frame relay network, and that some of those advantages are it's easy to scale, less cost from the form of network equipment and physical connections, and the ease of management. There are some downsides, and you do want to be aware of these when you're designing and when you're troubleshooting. There's the case that the single point of failure is on the access circuit on the hub, because the big thing to remember with hub and spoke is that all traffic goes through the hub. All roads lead to the hub. So your spoke-to-spoke traffic is going to traverse the hub. That's going to give you some cost savings, but it also introduces a couple of disadvantages. Again, the single point of failure on the hub access circuits, as well as the one we just looked at, whereas depending on how geographically close, it's not always a geographical issue, so I don't want to keep hounding that, but just know that your spoke-to-spoke connection may be quicker if you provision a virtual circuit between those spokes than it is when you go through the hub. In most cases it is going to be faster, but is it significantly faster? Is it worth provisioning an extra circuit between those spokes? Anyways, that's something you want to keep in mind for design. That's going to wrap it up. Next up, we're going to take a look at some configuration because we've gone far too long. I'm jonesing for some CLI action here. So once again, thanks for joining me in the Packet Lab. As always, I hope this helps you on your route to becoming a network guy.